Hello, everybody. My name is Masoud Olia, and I'm a professor here in School of Engineering at Wentworth University, and I'm here with another problem. I decided to do a problem on the subject of mechanics of materials related to the topic of uh, the principal stresses using the graphical approach, which is basically the Mohr circle. Uh, So I have this stress element. So let me actually remove my camera here for you and try to flatten my iPad so we can do the problem. So you see, this is stress element, which basically represents a point in a structure. For example, it could be a shaft, right? Under the action of, let's say, if it's fixed one end, you have a load here. Maybe you're twisting it. Maybe you have an axial load here. So this load here creates bending, right? The twisting creates, shear stress due to twisting, and then this axial load also creates, sigma. So the bending obviously creates the sigma equal MC over I, and this guy creates load over area, and then you can combine these and look at a point, a critical point, and then expand this point as basically a three-dimensional stress element, right? With these stresses acting on it, right? As you can see. But normally you don't need to look at a three-dimensional element. You could just look at the front face of this and reduce it to a 2D element. So I have actually videos on the topic of combined loading, which is what this is. Okay, so you can look at those videos. Just do a search on my channel for combined loading under mechanics of material, playlist. Anyways, so the objective here is to find the principal stresses. So principal, spelled like that. And the maximum, what we call maximum in plane shear stress. And we could actually use a graphical approach to show these different, stresses. All right, so the way you actually get the Mohr circle, now Mohr circle is just a graphical approach where it will show you actually what's happening at different planes, where your principal planes are. Principal means maximum, basically. And they're usually denoted by sigma 1 and sigma 2. Okay? All right. So basically, your reference is this side on this plane, which we call it point A. The coordinate of point A is always sigma x and tau xy. Okay? And by the way, if we go and define our stresses based on the way they're acting, sigma x is actually a positive 30 megapascal because it's in tension. Look at your sigma y. Sigma y is negative 20 megapascal because it's compressive. And this tau xy actually is a positive 80 megapascal. Basically, if you look at this side and your stress, the shear stress pointing up, that's a positive arrangement. This is positive, this is positive, and this is positive. Basically, this arrangement is positive. Okay? So back to point A, then point A has coordinates of 30 and positive 80, right? Sigma x and tau xy. Now, in order to draw a circle, which is known as Mohr circle, what do you need? You need coordinates of one point, and basically the location of center, point on a circle and the center, and then you can just connect center to the point and then draw the Mohr circle. All right, so center has always the coordinate of what we call the average stress, which is actually the average of the two normal stresses. So if we go ahead and add these two, remember one of them is negative, that becomes 10 over 2, 5 megapascal. So center then has coordinates of sigma average always and 0. So in other words, center always falls on the horizontal axis. So center has the coordinates of 5 and 0. So this would be good enough for us to be able to plot, to draw our Mohr circle. Now, you got to be careful. Positive sigma axis is to the right, but positive tau axis actually, because of the notation that we use, is downward. This is positive tau and this is positive sigma. So let's go ahead and locate center. So center is very close to the tau axis, right? Only 5. And then the coordinate of 30 and 80 for point A. So I'll say this is 30 and positive 80. Now this is not going to be to scale. I'll do my best. So we'll have something like this as point A. And then if we connect C to A, that basically defines the radius. So radius is CA, which happens to be what? You could actually tell from the coordinate that this is basically 30 minus 5, right? Remember, this is 30 basically, right? And this is 80, right? Squared and then 80 squared, right? So graphically, you can figure out the radius. So this comes out to be about 83.8 roughly megapascal. All right. So now, once you have that, let me actually do this. Extend this a little bit. So I have room to do this. Now, this is going to be tough to draw a circle, actually. I'll do my best. So this is really weird circle, guys. You have to forgive me for this. But look, guys, where this circle crosses the sigma axis, that becomes your sigma 1, because that's the maximum sigma that you can get. This is really messy. But, and this is your sigma 2. Actually, sigma and sigma 2 are easily determined by just saying, look, sigma 1 is C plus R. See, this is C, and this is R actually, right? And C minus R is sigma 2. So those are your principal stresses. So if you go ahead and have 5 plus what? R is what? 83.8. And then 5 minus 83.8. Sorry. 5 minus 83.8, right? So sigma 1 happens to be 88.8 roughly. So this is actually 88.8. And this guy would be 5 minus, so that falls on the negative side, is compressive, and that would be 78.8 negative, right? So that's your minus 78.8. So those are your principal stresses. And basically, this angle from this line CA to where your principal plane is known as 2 theta P, right? Because remember, everything in the Mohr circle is double angle. That's how it's actually defined. I would probably show you a video, or maybe I have one in the context of lecture during the COVID that showed how we can actually define Mohr circle based on the equations, transformation equations. But in any case, 2 theta P, you see tangent of this 2 theta P, which is the principal plane, becomes what? Becomes 80, right? Say 80 over 25, right? So this happens to be, if you do inverse tan, 2 theta p is going to be about 72.6 roughly. So the angle on the element, 36.3 roughly. Okay, so what I mean by that is that, look, if I redraw my stress element, which was like this, at what plane do I get this sigma 1 and sigma 2? Remember, your reference is always this point. So that means that actually you have to rotate, which way? Clockwise, counterclockwise, right? How much? 36.3. So if you basically rotate this plane, I have to actually move this a little bit down so I could do this for you, right? There we go. Maybe a little bit more down. Okay, so this is point A. So 36.3. So you see now, this is basically the angle really is this, 36.3, right? So this was point A here. Now look, this guy, 88.8 would be right here. And of course, it's going to be the same thing here. And then look, the difference between sigma 1 and sigma 2, you see, sigma 1 and sigma 2 is what? Is 180 degrees, right? But that's in the Mohr circle setting. When we come to the element, it's 90 degrees, half of it. So your compressive one will fall here, then 90 degrees to it, right? 78.8, 78.8. Remember, on the principal plane, shear stress is 0, because look at the coordinate of this point is what? 88.8 and 0. See, your tau is 0, right? So that's why you don't see any shear stress on the principal plane. Now, based on probably videos that you've seen, I have videos on that too. The plane of the shear stress, so this is where the maximum shear stress is going to happen. We call it theta sub S, S for shear. The plane of maximum shear stress is always theta P plus or minus 45 degrees. So you could think of it as, if you add to 36.3 a plus or minus 45, you could think of it as, 81.3 or negative 8.7. By the way, positive angle means counterclockwise, negative angle means clockwise. You see, from this plane, if you add 45 degrees to it, guys, right, or subtract 45 degrees, right, you'll get to here. So that's the plane of maximum shear stress. Look, what's the coordinate of that point? 0 and what? The radius, which is what? 83.8. And what's the coordinate of this point? 0 and minus 83.8. Remember, positive is downward for tau, right? So from point A, you can go 100, see, double this, 162.6, right? And get what? Here, or double what? 8.7, which is 17.4, and get to here. See that? All right, so the plane of maximum shear stress, just to show you, if you want to look at it, 45 degrees to this plane, right? So it's going to be something like this. So this is where maximum shear stress is going to be. I'm sorry, I made a mistake, guys. I wanted the coordinate of this point. Actually, that's where the maximum is going to happen. So this is actually, guys, sorry for that. That's 5. And that's also 5. Because these, the center was so close to the tau axis that I made a mistake. So that's a 5. All right. So basically what you have here is that the plane of your maximum shear stress which is 83.8, right? Something like that. That's your maximum shear stress. And it's all the same around the all four sides. And then also you have the average stress, which is actually the coordinate of the center. There we go. One interesting thing, guys, about these principal stresses is that if you add sigma x to sigma y, that should be the same as sigma 1 to sigma 2, and you can try that. You see here, sigma x to sigma y is what? 80 minus 20. If you also do 88, I'm sorry, 80, sigma x was 30, sigma y was minus 20. Sorry, guys. 30 and minus 20. So now do the same thing. Sigma 1 is 88.8, and then sigma y is 78.8 negative. So you see the end, they all come out to be 10. So basically what that says, it says that the sum of two normal stresses on 90-degree planes is a constant. And that happens also on this plane. Look, guys, 5 plus 5 is also 10. See that? So I know it was kind of maybe done fast, but as I said, I have more videos on this, so you can always refer to those videos. As always, I appreciate if you can subscribe to my channel and also like the video. Thank you very much, and I'll see you soon. Thank you.